In today's lesson, we're going to be talking about composition of functions. To start us off here and look at the operation of composition of functions, we're going to let f and g be two functions. X is going to come out of the domain of g, and g at x, i.e. the image when g acts on x here, is going to be coming out of the domain of f. So both of these conditions have to be satisfied, and you'll see why when we look at what the definition of composition means, why you need these two additional conditions on top of f and g being functions. So composition of functions notationally looks like this. And how this works is this is read as f composite g. This is your composition symbol. It's not a zero. So f composite g acting on x by definition is the function g acts on x first. And then the image of that, i.e. g at x, becomes the input for my function f. And then f would act on g at x. So if you take a look here, you can see why right away your x value, since the function g acts on x first, x has to be in the domain of g, else the function would not be defined. Then wherever g sends the function x, i.e. notationally g at x, that has to be in the domain of f. Because what the function f is going to do, it's going to take in that g at x and act upon it. So that g at x has to be in the domain of f. So that's the reason for these two conditions here in addition to f and g being functions. So this operation here is called composition of functions, and just like when you add two functions, subtract two functions, multiply two functions, or divide two functions, you get a function as your output. Same thing works here for composition of functions. The composition of two functions creates a new function. Let's take a look at some examples. For our first example here, we have a function f, which is x squared minus 1, and we have a function g, which is a linear function 2x plus 1. We want to look at what is f composite g. Well, by definition, we just studied this. F composite g is going to be f acting on g at x. So therefore, we're going to have our function f. Well, g at x is 2x plus 1. And now we go back to our function notation lesson. So in this example here, everywhere you see an x for our function f, we're going to change that to a 2x plus 1, in which case we get 2x plus 1 quantity squared minus 1. Expanding this out, you square the first times second times 2, and square the last. And simplifying a bit, we have that f composite g is equal to 4x squared plus 4x. So this is the new function we've created here. This is at 4x squared plus 4x. Let's take a look at another example. All right, take a look at our next function here. We've got, this time we want to calculate g composite f at x this time. Well, by definition, this is going to equal g acting on f at x. And recall here we have f at x is x squared minus 1. So there this becomes g acting on x squared minus 1. And going back to function notation here, everywhere we see an x, we're going to change that to an x squared minus 1, in which case we get 2 times x squared minus 1 plus 1, which is 2x squared minus 2 plus 1, which is 2x squared minus 1. So therefore we have here g composite f at x is 2x squared minus 1. So first observation here, which is an important one, notice that g composite f at x and f composite g at x created different functions. Therefore, we say that composition of functions is not a commutative operation. So the idea of commutative operation, in this case, we mean that g composite f is not in general. There are functions where that is true, but in general, it's not equal to f composite g. We do have some commutative operations we've discussed, like for instance, f plus g is going to create the same function as if you take g plus f. And likewise, f times g is going to create the same function if you take g times f. We have also studied other non-commutative operations. For instance, f divided by g is not in general going to create the same function as g divided by f. And lastly, f minus g is not going to create the same function as g minus f. So we have some functions we've discussed that are non-commutative, these two here, and are now our composition function. And then we have these two functions right here are commutative operations for functions. All right, let's take a look at g composite g at x. So again, by definition, this is g acting on g at x. And in which case here we know that gx is 2x plus 1. So now everywhere we see an x, we're going to change that to a 2x plus 1. And expanding this out, we get 4x plus 2 plus 1. And our new simplified composed function, g composite g at x, in this case here is going to be 4x plus 3. Let's take a look at another example. So continuing this on here, we want to do g composite g at x. Well, by definition, this example is kind of showing you that you can compose this function multiple times. The composition function can be done iteratively. So in this case here, this is going to be g acting on g at x is 2x plus 1. And now we just figured this out already. We know that when g acts on 2x plus 1, or in other words, when g acts on g at x, we just did that in part C, we know that that's going to equal 4x plus 3. And now everywhere that I see an x, I'm going to let that be a 4x plus 3. And you can see here I get 8x plus 7. Let's take a closer look at this iterative composition of just the function g. All right, putting these together here, I just want to make the following observation. We had g at x is 2x plus 1, g composite g at x is 4x plus 3, and g composite g at x is 8x plus 7. This will continue on, and there actually is a pattern to this here. You'll notice we got 2, 4, 8, 1, 3, 7. Yeah, you can make a conjecture yourself as to what you think the fourth composition, fifth composition, and then finally the nth composition. You can generalize this statement to the nth composition. All right, let's take a look at another example. So in the following example here, again, we're given two functions. One function is square root of x, and the second function is negative x squared minus 2. Let's take a look at what f composite g would be like this time. So this will be g composite g at x, which everywhere I see g at x, I'm going to change that to a negative x squared minus 2. And now, like we talked about, everywhere you see an x, it's going to be equal to the square root of negative x squared minus 2. So this is our composed function here, f composite g. All right, so just another example going through composition of functions with roots involved. Notice the domain here would be a little bit different. If I want to calculate the domain of this, what's underneath the square root sign, in this case negative x squared minus 2, that must be greater than or equal to 0. So it must be the case that negative x squared minus 2 must be greater than or equal to 0. So doing a quick sketch of this function, something interesting happens. As I graph the negative x squared minus 2, we notice that it's actually always below the x-axis, which means that this expression itself is always negative, which means that the square root of this function always does not exist in the real number system. So therefore, f composite g creates a function where the domain can be no real numbers. So in this situation here, f composite g does not exist as long as the input is real numbers. And we'll talk a little more detail later about complex numbers, but for now we compose these two functions. We created a function, however, this function doesn't exist in the real number system. So here's an example where the domain sort of falls apart when we compose the two functions. Let's look at another example. For the following example here, they give us our reciprocal function and then a quadratic, and they want us to find a bunch of evaluations of the function here. So f composite g at 1, f composite g at 1, etc. So there's two ways you could write this. One way you could write like this, f composite g at 1. Also, equivalently, it can be written as f composite g, all in brackets, acting on 1. These both mean the same thing. I thought I'd point that out notationally, but at any rate here, this is going to equal f composite g at 1. Well, g at 1 is 1 over x, but that x is now a 1, so that's going to be f at 1 over 1, which is f at 1, and now this will be 1 squared minus 1 plus 1, and the output is a 1. With this one here, this will be, and again, notationally, you could have written this as f composite g acting on 1 equivalently, but for this one here, this will be f acting on g. G at 1 we just discussed was 1, and again, g at 1 is 1, and f at 1 we just discussed was also 1. So notice both of these compositions had the same output. Let's take a look at some more. So this one here, we want to do f composite f acting on 0 this time. So this will be f acting on f at 0. Okay, well, what's f at 0? Well, f at 0 is going to be, everywhere I see an x, I'm going to be changing that to a 0. So this will be 0 squared minus 0 plus 1, which is f at 1, which again we know is 1. Let's take a look at this one here. Again, alternative notation, if you are looking just for different ways of representing this, you could write this as negative 2 times f composite g at a half as well would be an equivalent form of writing this. Now again, When you apply, like you have multiplication by this -2 in front, you're going to take care of your composition first. And that -2 is multiplication. You save that for the end. So if I'm going to evaluate this here, it's going to be -2 times f acting on g at a half. Okay, well, what's g at a half? Well, it's going to be -2 times the function f acting on g at a half is going to be 1 over 1/2. And as you know, when you divide by fractions, you multiply by the flip. So this is equivalent to being f at 2. Well, f at 2 is going to be -2 times 2 squared minus 2 plus 1. And we get -2 times 4 minus 2 plus 1, which is -2 times 3, which is -6. So now we have here f composite f at 0 is 1, and -2 times f acting on g at a half is -6. Let's take a look at some more examples. So continuing on here, we want g composite f at 0, and this is going to be g acting on f at 0, while f at 0 is going to be 0 squared minus 0 plus 1, and as you know, that's equal to 1, and g at 1 is 1 like we discussed earlier. So once again, we get 1. So for the following example here, again, we're studying composition of functions, but we've kind of looked at it in terms algebraically. You can also talk about composition of functions from a diagram itself. So this time here, we want to do g composite f at x, and where our x value is 6. Well, let's take a look. This is going to be g acting on, what is f at 6? Well, my function at 6, you can see your function f is outputting a 4. So this will be g at 4. Well, what's g at 4? G at 4 outputting up here is going to give us a 2. So therefore, g composite f at 6 is 2. Likewise, you want f composite g at 7. So this would be f composite g at 7. And now you'll take a look here. G at 7, everywhere we see, where we see a 7 here, I have a 7 here. G is outputting a 2. And now we want to look at the function at 2. Well, the function at 2 for f is going to output a 1. And we're done. So therefore, f composite g acting on 7 is 1, and g composite f acting on 6 is 2. Okay, in our final example here, we have two functions, f and g. We want to take a look at operations using f composite g, for instance. Now, first we want to take a look at the domains here. Because remember, the definition is you have two functions, f and g. F and g have to be functions, and it has to be the case that x has to be in the domain of g, and we had the added condition g at x has to be in the domain of f. Okay, let's take a look at what the domain of f and g are. Well, domain of f here is equal to 1, 3, 5, and 7. The domain of g has to equal 0, 1, 5, and 6. So right away, notice some observations here. When g acts on 0, it outputs an 8. When g acts on 1, it outputs a 3. When g acts on 5, it outputs a 1. And lastly, when g acts at 6, it outputs a 5. 8 is not inside the domain of f. So therefore, this value here cannot be part of our input for our composition of functions. 3 is inside the domain of f. 1 is inside the domain of f. And 5 is inside the domain of f. So therefore, we can talk about all of these. All right, so let's take a look at some operations. All right, so let's take a look here. So I got f composite g at 1. So by definition, that's going to be f acting on g at 1. As we just discussed, g at 1 is 3. And that's okay because 3 is inside the domain of f. Well, where does 3 go? 3 goes to -4. Let's take a look at another example. So this would be f composite g acting on 5. So this would be f acting on g at 5, which again, g at 5 we just discussed has an output of 1. And now when f acts on 1, we can see here 1 is being sent to 2. Continuing on here, we have f acting on g at 6. Well, g at 6 is going to be equal to 5. Now when f acts on 5, we have the output is a 6. So f composite g acting on 6 is 6. F composite g acting on 5 is 2. And f composite g acting on 1 is -4. All right, that concludes today's lesson on composition of functions. Thank you.